so now we will start with the class C power amplifier. It is also called as tuned amplifier, because the definition, what the definition of class C amplifier says, a amplifier is said to be class C power amplifier. The input signal and the Q point are selected in such a way that the output signal is obtained for the input less than 180 degree and the Q point is shifted below the x-axis. Okay, so that's the definition of class C amplifier. So it's nothing but here when for the less than 180 degree input cycle, class C amplifier will be in the active region. So remaining time it is off. So for a particular value of input, it is on and provides the gain which is maximum. So that's why it is a tuned amplifier, because for a particular frequency of the input signal, the gain of the power amplifier is maximum. Remaining time either it is decreases or remaining time it always decreases. Okay, so that's why it is called as tuned amplifier, and these amplifiers are specially used in the radios, okay, to set a particular tune to listen for the particular music or some programs in the radios like 93.5 FM. So like this, for a particular frequency, this amplifier has a maximum gain. Remaining time it is always decreases. Decreases means there it has a maximum distortions. Only for the particular frequency it gives us a particular or pure output. So that is class C amplifier. That is explained in the resonant frequency circuit. Here class C tuned amplifier. So here it consists of at the input side Vin, then there is RFC choke to block AC and allow DC, NPN transistor, a parallel resonant circuit, and the load resistance RL with the coupling capacitor CC. Now, what is the role of this parallel resonant circuit? It is a circuit which acts, this is a parallel resonant circuit which acts as a load tuned to the input frequency. Means it filters the harmonic frequencies and produces a particular sine wave which at the output side, considering only the fundamental component of the input signal. Nothing but here this acts as a filter, this circuit acts as a filter to remove the unwanted information present in the output signal with respect to input and generates only the fundamental frequency which has our original information. This fundamental frequency for a particular resonant frequency or for a particular value of L and C. Through the coupling capacitor and load resistance RL, we can get this waveform. So this is how the circuit works. Only less than 180 degree of this input, we will get this output. Okay. So now here that same thing is explained in the waveform representing class C operation. This we already discussed in the classification also. Here this is a Q point which is shifted below the x-axis, which indicates that the circuit belongs to class C amplifier. This is a collector current which is less than 180 degree, okay, along the VC axis and IC axis. Okay, this is what we already discussed. So this represents the waveform for class C amplifier. And here this is the resonant frequency. We already derived the expression using Hartley oscillator and Colpitt's oscillator or crystal oscillator. The frequency of oscillation is always, if there is a L and C circuit is there, it always depends on 1 by 2 pi square root of L into C in terms of hertz. So this is the resonant frequency which is obtained by LC and the RFC choke which is connected with respect to input. Okay, so now this is about the formula, and here what I explained this is a frequency response curve with respect to input or with respect to frequency and gain here. So here as the frequency of the input signal increases, the gain of the class C amplifier increases here and reaches to the maximum value which is shown here. This is a maximum value where the gain is maximum. So at this time the class C amplifier produces its output which contains only fundamental frequency which has the information. Again then after some increase in the frequency at the x-axis, again it starts decreases. Means this part and this part contains only the distortions. Only at this part it gives us a maximum gain, okay, with the fundamental frequency or the resonant frequency. Hence, for this amplifier, it has 100% efficiency, but it includes a lot of distortions in the output. Okay, so this is what the frequency response explains. Now, we'll move on to the load line, means the nomenclatures. Here we'll discuss them briefly. Okay, this is a load line. This is the resistance RS here. Load line means it includes both AC and DC signal or AC and DC load line. Here this is a RS, series resistance of inductor. Here you have to assume that there is a LC circuit connected. This is the resistance RB provided for the RFC choke. Okay, here it's only a DC circuit. If I consider it for AC, there is one coupling capacitor here and the input signal connected here. Because of the DC equivalent circuit, it is eliminated. Only the resistance RB provided by the RFC choke, resistance RC in series with the inductor. This one I am explaining here. This one. So this is the RFC choke, provides the RB, VN and coupling capacitor are neglected, and this L and C in that resistance RS is connected in series with the L, because here in the DC circuit they are all neglected, only the respective resistance are mentioned in the DC circuit. Okay, and this RS value is very small, hence assumed to be 0. That's why the DC load line is a vertical straight line. This is the AC load line between IC and VCE, where with IC value is VCC by RC. This RC is a AC resistance of the resonant frequency. Okay, we will determine how to find the value of RC in the next nomenclature. Now, after this is about load line here. Okay, a brief explanation. Now we'll move on to the AC equivalent circuit. So this equivalent circuit is drawn based on the DC and AC equivalent circuits, or AC circuit which is shown here. It is drawn using this circuit and it is drawn using this circuit. Both circuits are utilized to draw the AC equivalent circuit. Now look at this circuit. Here this is a V-in coupling capacitor as I explained, RB resistance shown in the DC. This is the diode connected between the base and emitter of transistor, this one. Between the base and emitter, this part of this transistor is replaced by a diode. Okay, this is replaced by a diode. Now base to emitter connection. Similarly, this is a current source between the collector to emitter, means this part. So here this part of the transistor is replaced by current source, and this part of the transistor is open circuit when it is conduct or when it is active region, open circuit. That's why it is shown here. It is open circuit here. This is collector to emitter replaced by current source like beta into IB. And here these are the inductor and capacitor connected in parallel, which is shown in the class C tuned amplifier. This is a series resistance connected with the inductor, and this is a load resistance with the RL. Okay, the AC equivalent circuit is drawn using these two, DC and class C tuned amplifier. Here RS is replaced by the parallel RP resistor. So both are same equivalent circuit. This output circuit, this output circuit are similar. Only the change is we can replace RS by RP, where RP is parallel with inductor, RS is in series with inductor. Both provides the same output. Now some formulas are directly considered here, where QL represents the quality factor of an inductor, depends on the resistors and the reactance present in that inductor. That is the ratio of XL by RS. Okay, this is a quality factor of the inductor which is used in the circuit. This is XL is nothing but omega L. R represents the resonant. So omega R into L is a resonant angular frequency. L is the inductor. RS is a series resistance, which is explained here. Okay. Now RP is parallel resistance, which is in parallel. So just you have to reciprocate this one. So this becomes, if in terms of RP, this becomes RP by omega R into L. If I do that, we will get this expression. Okay. This expression is just reciprocating this expression, replacing RS by RP. Now we know that RC is the AC resistance of the collector at resonance, which is always equals to RP parallel with RL. Here there is no derivation is taken. Only to just mentioning the concept, we have taken the expressions. Therefore, we can write the Q factor with respect to RC and omega R into L. So like this. This is a Q factor of the overall circuit with respect to AC resonant and inductance. Now, the next nomenclature is DC clamping of input signal, and in this signal, now here only we have considered the input part of the AC equivalent circuit. Okay, this part we have considered, and I will explain why it is called as clamping circuit here. We call it as DC clamping of the input signal because this is the input signal which is applied for the AC equivalent circuit with the amplitude of plus Vp to minus Vp. And here what it consists at the input side, input signal, coupling capacitor or the input capacitor, RB resistance, input resistance, and one diode between the base to emitter taken place here, emitter diode. So now when the input signal is applied or during the positive cycle of the input signal, here capacitor gets charges through the diode because diode becomes forward biased during the positive cycle. This cycle diode is on, capacitor charges. During the negative cycle, this part of the cycle, here diode becomes reverse biased, capacitor discharges through the resistance RB. Now here capacitor discharges during negative cycle. Therefore, here the capacitor, the discharge capacitor value is added with the output cycle. Hence, the output cycle will clamp towards the negative side. Getting what I am saying? Here, this is the cycle which is present at the positive side. Now, this is the total cycle which is at the negative cycle because capacitor discharges during negative cycle. That DC value adds to the input signal and makes to clamp towards the negative side. Okay, actually there is expressions here. So here just concept I am going to explain. So that's why, and this part is here, only this part, it means from 0 to T and above, this part is used just to, which is less than 180 degree, used to turn on the transistor. This part is just clamped to or shifted towards the negative side with the amplitude of Vp, that is minus Vp and minus 2 Vp. Okay, this is the input, and we will get the output exactly opposite to this. Okay, that I will explain sooner. Now, like this we are getting the input cycle which is less than 180 degree from this AC equivalent circuit, input side of the circuit. Now, we will move on to the next, that is filtering the harmonics which are present in the input cycle. So this is the input cycle which is as current pulse is here less than 180 degree. This part of the cycle I have taken here, this one. Okay, filtering the harmonics means is there any harmonics are present or distortions present in the input cycle. If they are, like if f is the fundamental frequency, has the original information, 2f, 3f up to nf, these are the harmonics which are not required. We have to check that if they are present. If they are present, we have to remove them using this output circuit. So this is the output circuit which is used in that L and C are used to filter any harmonics present in that circuit and produces the output waveform here. So here output waveform is exactly opposite to the input because there is 180 degree phase shift. So this is, here we have written minus Vp minus 2 Vp, and here I have written Vp is nothing but maximum peak value, that is VCC. Here we written 2 VCC, VCC starts with VC saturation, exactly opposite. This is a output or collector voltage which is pure sine wave. Okay, now the next nomenclature is bandwidth. Bandwidth is nothing but F2 minus F1, which is shown also here. This is already known, and bandwidth can also be defined using quality factor with the resonant frequency. This is defined here. Okay, the next is duty cycle. It is defined as the ratio of on period of the transistor to the total period of the pulses, which is written here W by T. Okay, and here this is the W, this is the total time period. So that the ratio gives us duty cycle, and that can be also represented using an angle. W is a time which is required to generate a on cycle. 360 degree is a total complete cycle utilized. So D is nothing but pi by 360 degree is used to generate the duty cycle. Next is the output power. As we know the definition, power means voltage into current, and here it is written in terms of VRMS square by RL, because IRMS equals to VRMS by RL. In terms of V to peak to peak, you know that V peak to peak is nothing but 2 Vm, or in other terms you can say that Vm equals to V peak to peak by 2. Here it is written V peak to peak equals to 2 Vm, where Vm is nothing but what? Root 2 into VRMS, or we can write VRMS equals to Vm by root 2. In other terms, it is written Vm equals to root 2 into VRMS. That is substituted in the V square RMS, and we get 8 VPP square root by 8 RL. Just the substitution is done here, nothing important. That is the output power. Next is transistor dissipation. Maximum dissipation occurs when it reaches the resonant frequency here, and here that is shown here. At this time the maximum power dissipation occurs. This is the maximum output, which is already explained. This is a collector current, and this is the maximum power dissipation occurs when IC equals to IC saturation. Okay, so therefore the maximum power dissipation formula is this, which is nothing but V square PP max by 40 RC. This is directly written here because there is no derivation here. And here this graph indicates that when the input signal is at 180 degree, we get the maximum power dissipation occurs, because at this time there is a output, we will get the maximum output because of that maximum power dissipation. The next is here DC input power. So in this DC input power, the current IDC depends on I saturation by pi. I saturation is nothing but here Im, the maximum peak value. Okay, so IDC equals to IC saturation by pi, like a half wave rectifier output, which is 1 by pi is nothing but 0.318. So therefore PDC is nothing but VCC into IDC. These are all similar to the transformer coupled push-pull class B amplifiers. What we discussed, same waveforms has been, or expressions has been written here. The next is last, the efficiency, nothing but AC by DC. P out is the AC output power, PDC is the DC input power. Substitute here, we will get the percentage efficiency of class C tuned amplifier. And here in this graph it is explained that when the input signal is at 180 degree, or the angle is 180 degree, here we can reach 78.5% practically if the angle is reduced. If the pi is reduced, or for smaller pi we can reach up to 100%. Only the problem is it has major distortions present in the output. So this is about class C tuned amplifier. Okay, so this completes your module 3. Okay, if you have any doubts, you can free to call or message me so that we can clarify your doubts. Thank you.